Okay, so we've come to question 2, and if we read what it says at the beginning, it says hemiacetals and acetals. So even before we get any further, we're already struck by the fact that we have two terms that we are unfamiliar with. These are not things that feature in our A-level chemistry specification. So let's carry on. Let's carry on and see then what follows. So it tells us that they are compounds formed by the reactions of aldehydes with alcohols, and we are familiar with aldehydes and we are familiar with alcohols. And then they give us a particular examples. They give us ethanal and ethanol. So we have got two things that we are familiar with: ethanal and ethanol, or an aldehyde and an alcohol, reacting together to form a product that we are unfamiliar with. So looking at this equation, we have two reactants, we have one product. That straight away tells us that this is an addition reaction, because we only get one product from two reactants. Something else to just sort of point out is all of this information that we're being given at this beginning here could be read, it all features, before any of the actual questions. So this is information that could be relevant to any of the subsequent questions, any of them. So we could get to the very end. We might have been working through a number of questions, and then the fiery final question still may refer to something that features at the beginning here. And that happens quite often. Sometimes exam questions can be over a number of pages, say 3 or 4 pages. You get to the 4th page, you're answering a question on the 4th page, but you might still need to refer back to what was right at the beginning, the information that you were given before any of the questions started. So we have an aldehyde and an alcohol reacting together. If we think about which parts of the product have come from the aldehyde and which have come from the alcohol, then our aldehyde is clearly that. And then our alcohol let's get that highlight white. That's from our alcohol, but that hydrogen must be from our alcohol as well. So that's just something to bear in mind, I think. Okay. So we've made sure we've understood, or at least partially understood, or we've recognised what we can understand, perhaps is the best way of putting it, what we could have got from that first bit of text, that first bit of information. So now we come to the very first question, and it says, use your knowledge of carbonyl mechanisms. And if we think about the carbonyl compounds that we have studied at A-level chemistry, they are aldehydes, ketones, and then the carboxylic acids and derivatives. Now we have an aldehyde here, so we're clearly talking about a carbonyl mechanism relevant to an aldehyde. So it's our sort of appreciation or knowledge of carbonyl mechanisms. And then they use a word which crops up quite a lot in exam questions, and typically this word suggest. Typically when they use the word suggest, that normally means that this isn't something that we have absolutely directly done or absolutely directly features in the specification, but which they believe you can apply your knowledge from what you've learnt to this particular context. So it says, use your knowledge of carbonyl mechanisms to suggest the name and the mechanism of this reaction. Well, we know it's an addition reaction. We've established that even before we've got to this part. And if we think about all carbonyls, whenever we have done any mechanism featuring a carbonyl group, it has always been nucleophilic. It's always been a nucleophile, that's an electron per donor, attacking the delta positive carbon of the carbonyl group. So we have not done the reaction above, but they've given us some guidance. We apply the knowledge that we have or know, and we can be pretty confident that we're talking about nucleophilic addition here. All right, so the next part of the question. So it says we need to outline how an ethanol molecule reacts with an ethanal molecule in the first step of this mechanism, so the mechanism that we've suggested above, which is nucleophilic addition. include two curly arrows to show the movement of the electron pairs. So I think the first thing, we know that it's the carbonyl that gets attacked, so I think the first thing I'm going to do is draw the aldehydes, which is ethanol. And we know it's the ethanol that's reacting with it, and we know that the carbonyl, it's nucleophilic addition, so the ethanol must be acting as the nucleophile. We know that a nucleophile is an electron pair donor, so we must be thinking about where the electron pairs are on the ethanol molecule. It has to be a lone pair. And we can think that oxygen, providing it has its normal two bonds, always has two lone pairs. So I'm just going to draw one of them. And then we're to draw the two curly arrows. And, you know, actually, even if we were thinking about, even if we'd put nucleophilic addition elimination, perhaps we'd mistakenly put the wrong mechanism above. The first two arrows for both nucleophilic addition and nucleophilic addition elimination, the first two arrows are the same. So we have an arrow from the lone pair to the delta positive carbon, and then we have an arrow, a second arrow which shows the movement of the pi electrons onto the oxygen. And there we go, there's our answer to that question. So we might have been thrown by what it said right at the beginning, but actually this is a question so far about aldehydes and ketones in terms of the topics that we've done. Okay. So the reaction produces a racemic mixture of chiral molecules, and then it asks us to explain the meaning of the term racemic mixture. And so the key thing here is the racemic part of it, and our answer to that is going to be that there is an equal mixture. Well, sort of, that's slightly a tautology, isn't it? But it's the racemic bit that's important. Now, the equal is very, very important. So you must say equal, or you must make it very clear it's equal. So another way you could express equal in this instance is to say it's a 50-50 proportion or something, or a 1-to-1 proportion, something like that. But of what? So they're chiral molecules. What are we talking about when we say chiral molecules? We're talking about optical isomers, but I'm going to use the word enantiomers. Okay, so there's an equal mixture of enantiomers, but the equal bit is absolutely crucial, absolutely fundamental. Then it asks us to state the relationship between two chiral molecules with the same structural formula. So whenever we have molecules with the same structural formula but which are different, then they must be stereoisomers. So they have the same structural formula but a different spatial arrangement. We have two types of stereoisomers. We have geometric, which come about when we have a carbon-carbon double bond, because there's the restricted rotation of that bond. And then we've also got optical isomers. And if we're talking about chirality, we're clearly talking about optical isomers. And if we were trying to show, these two chiral molecules, and you think about how you would do that, you would do it by drawing mirror images, and that is what they want here. So they want the fact that these molecules are mirror images of each other. Now that would be enough to get the mark, but I'm just going to add something before that because I think it's an important thing to stress. Because how can we make it clear that they have a different spatial arrangement? So saying they're mirror images doesn't absolutely fundamentally say that. But if we made it clear that they were non-superimposable, then we would be making it clear that those mirror images have the same, well, they had a different spatial arrangement. Okay, so let's move on to the next part then. So in the presence of an acid catalyst, such as hydrogen chloride, ethanol reacts with an excess of ethanol to form an acetal. The overall reaction of ethanol with an excess of ethanol forms an equilibrium mixture as shown. All reactants and products are liquids. So they give us an equation, a reaction equation, and then they give us some data regarding how many moles of the reactants there were before the reaction took place, and then they give us information on how many moles of one of the products there is once equilibrium has been reached. So this is an equilibrium question. So, you know, this is an example of where organic and physical, you can have aspects of both within a question. Now, whenever I have a reaction equation that I'm going to have to use, I always write above the actual molar ratios. So you may feel that all I'm doing is repeating what the equation says, and that is true, but I feel that sort of just lifting out those ratios just means I'm going to see them or think about them much more quickly when it comes to doing the calculations that I need to do. This is an equilibrium question, so please remember to use the ICE acronym for your as a way of structuring your working out. So ICE, and the I stands for initial, and that's where we're talking about the initial moles. C stands for change, so how the initial moles change. And then E stands for equilibrium, how many moles we have at equilibrium. Okay, all right, so let's now just write the information that they actually give us. So they tell us a mixture of 0.75 moles of ethanol and 5 moles of ethanol were left to reach equilibrium. So those are the quantities before those two reactants were mixed. So there are initial quantities. And if they haven't mixed, that means the reaction hasn't taken place. So clearly our products must be 0. We haven't made any yet. And then the other value they give us is the number of moles of acetal at equilibrium, which is 0.42. So we can see very easily that the change in acetal is 0.42, or an increase of 0.42. And I'm going to do water. You don't need to do water to work out the rest of this question, but I'm going to do it because it sort of makes the point about how this works. We have a 1-to-1 ratio when we look at our reaction equation on our molar ratios, a 1-to-1 ratio of acetal to water. So that means we expect the change in water to be exactly the same. And therefore we have the same number of moles because they both started at 0 of water as we have of acetal. So now let's look at ethanol. So if we compare acetal and ethanol, it's a 1-to-1 ratio. So that means that the number of moles that were made of acetal must have been the number of moles that were used up. It's a 1-to-1 ratio of ethanol. So we're going to have minus 0.42. So that gives us a final equilibrium value of 0.33. And then we can use ethanol and ethanol as a comparison. It's a 1-to-2 ratio. So that means the change in ethanol must be twice the change in ethanol. So minus 0.84. Then that gives us our equilibrium values of 4.16. And now we have our answers. So if you can, my advice to you is always to try, if you can, to put that ice where the equation is, like I have. It's not a lot of space. It might be a bit too cramped, I understand that. But if you are able to do that, it means everything that you need, all the information that you need is together. I've written that in the wrong place, sorry about that. Everything is together, and so I just think it makes it a lot easier to work out, basically. All right. So, in a different experiment using the same reaction as in part C, an equilibrium mixture was established at a given temperature. This mixture contained, and then they give us the values that the mixture contains at equilibrium, and they give us a total volume. So one thing to say is that in any question, if they give you a value as a piece of information, you will have to use that value. So if you answer a question and you discover at the end, once you've finished, that you have not used one of the values that you were given in the information, you have definitely made a mistake. So we are, in this example, we're given a volume So we're going to have to use the volume. And if we look at it, we see straight away it's in centimeters cubed. And whenever we do calculations in chemistry, we don't do those in centimeters cubed. So even before I think about the actual calculations I'm going to do, I'm going to change that to decimeters cubed, because that's the unit that we use, the unit of volume that we use when we're doing calculations in chemistry. So I'm just getting everything ready so that I can just focus on what it is I have to do when I have to do it. So they've given us those. They've given us the number of moles of the different substances. They've given us the total volume, and now we're getting really to the question. So it asks us to write an expression for the equilibrium constant for this reaction, then calculate a value for Kc at this temperature, and then give units with your answer. So to avoid the possibility, or to reduce the chance of us missing something when we actually write our answers, I think it's helpful sometimes to write numbers like what I have done just here, to say, okay, the first thing I'm going to do is write an expression. Second thing I'm going to do is calculate the value. And then the third thing I'm going to do is give the units. And if I write those 1, 2, 3, then what I can do when I finish my answer is I can check, have I done 1? Have I done 2? Have I done 3? It's just making it more overt and less likely that we're going to forget to do something that it's asked us to do. So quite often students will lose 1 mark maybe because it said name and outline and mechanism, and they forget to name it. And we could have put a 1 next to name, and we could have put 2 next to outline or something. Anyway, so it's asking us to write a Kc expression for the equilibrium constant for this reaction. So we're referring back to the equation that we saw in the calculation we just did in the previous part. And remember, Kc expressions, or any equilibrium expressions, are always about the concentration, or if in partial pressures in the case of gases, but of the substance. So we're always giving the formula of the substance. We're never putting any numbers in an expression. An expression is never something with values in it. And you remember that we put the products over the reactants, and we raise them to the power of whatever the stoichiometry is, whatever the molar ratio, or the molar ratio value is before the substance. So one of the products was acetal, and it was a 1 molar ratio, so it's to the power of 1, so we don't need to write anything. And the other second product was water, and again that was a 1 molar ratio, so it's to the power of 1, so we don't put a value. And then our reactants were ethanol, and that was a 1 molar ratio, so that's to the power of 1, and ethanol, and that was a 2 molar ratio, so that is to the power of 2, raised to the power of 2. Now, if you ever get a question like this, where they don't give you the volume, that can throw students sometimes. And if that happens, what you want to do to double check and be confident that that's okay is look at how many moles there are on each side of the equation, of the reaction equation. And if the total number of moles, is the same on both sides. So I'll give you an example. So a carboxylic acid plus an alcohol goes to an ester and water. It's a 1 to 1 to 1 to 1 ratio. So we have 2 moles on the left, 2 moles on the right. That means the volumes would cancel out, and so you don't actually need the volumes. So if we were doing the calculation, we would put, and we included our volume, they would actually cancel out, so they wouldn't be needed. So if you're not given the volume, check that the number of moles on both sides of the equation are the same, and if they are, that's why you weren't given the volume. It's not needed, but it is needed here because we have 2 moles of products to 3 moles of reactants. All right, so now we have to do the calculation. The concentration of the acetal is the number of moles of the acetal, which is 0.37, divided by the volume, which we worked out ahead of doing this calculation. Makes our life a little bit easier. Times the concentration of water, which again is the number of moles, 0.65, divided by the volume, which is the same volume, 0.310. And then that is obviously over the concentration of ethanol, which is 0.58 over 0.310. And then last but not least, ethanol So 3.76 divided by 0.310 squared. Okay. And then that gives us a value of 9.1 times 10 to the minus 3. Okay, so I'm just going to move that over to the side. And let's just see what we've done so far. Well, we have done the expression, and then we have done the calculation, but we've still got the units to go. So thinking about the units, what we do is we put the units for each of the terms in, and then we cancel them out. So I'm going to show you a method which might make it a little bit easier for you. If you don't find this useful, then just ignore it. But what I'm going to do is I'm going to let y equal moles per decimeter cubed, and then I'm going to put y in my equilibrium constant expression and focusing just on the units. So if we're thinking about the units now, we've got 1 mole. Oh, sorry, it's the units of, it's acetal, so that it has the units of moles per decimeter cubed, and it's to the power of 1 times water, which is also moles per decimeter cubed, and then that is over ethanol, which is moles per decimeter cubed, times the concentration of ethanol squared, so moles per decimeter cubed squared. So that equals y squared over y cubed, which I can simplify, and it's 1 over y. And now I put back in what y is. So it's 1 over moles per decimeter cubed. And then I am simplifying that again. So moles to the minus 1 decimeter cubed. So we reverse the signs. If we've got 1 over something, we just simply reverse the signs, or we make a positive a negative and a negative a positive. Maybe that's a little bit confusing, so apologies if it is. But anyway, we've arrived at our units, and our units are moles to the minus 1 decimeters cubed. And that is the third part of the question. So now we've done our 4 marks. So thinking about where those marks would come from, you would get 1 mark for the equilibrium expression, 1 mark for writing out the correct calculation, like the actual sum, a 3rd mark for the correct answer to that calculation, and then the 4th mark obviously for the units that we just did last. Okay, and now we come to the final part of the question. So it asks us to draw the structure of the acetal, and they give us a molecular formula formed by the reaction of ethanol with ethane 1,2-diol. Right, I'm not going to lie, this is a hard question, and I'm going to go through it really quite carefully, and in a real exam you wouldn't be able to spend the amount of time that we're about to do. But it's really to help you maybe appreciate better how you could perhaps go about answering this question, which you'd hopefully do faster by the time you'd finished your course. And if this question like this appeared in the final exam, you would be at your peak in terms of your understanding and knowledge. And obviously you're not there yet. But if the worst comes to the worst, it's 1 mark, and this is a mark that a lot of people won't get. So it's not the end of the world not to get it. So they've given us a molecular formula, and I think it's going to help me to appreciate, I think, the actual reaction equation in terms of elements, thinking about whether there's a second product and so on. So I'm going to write the formula of ethanol, and then we know it's reacting with ethane 1,2-diol, and we know it's making this acetal with this number of carbons, hydrogens, and oxygens. So yes, this is not a very good equation where I'm mixing molecular and structural formulae, but still, it's only to get an understanding of where we might be going with the answer. So if I look at what we've got on the left-hand side and compare it with the right-hand side at the moment, we've got 4 carbons, so that's great. If we then look at the number of hydrogens, We have got 10 on the left and currently only 8 on the right. So we've clearly got to have another 2 hydrogens. And then if we compare the number of oxygens, the final element, there are 3 on the left and currently 2 on the right. Sorry, I've miswritten the formula wrong again. Sorry about that. So 2 on the right. So that means we need another one. I think if it's 2 hydrogens and an oxygen, we can be pretty confident it's water, but also the equilibrium equation from earlier. Made it clear that water could be a product. And so now we've got to think about the structure. And if we think back to the very original equation, the thing that I said, the information that was given right at the beginning, and I said could feature it in any part that followed. If we thought about, in fact, let's just have a go back to it. If we thought about what was happening here, we said it was nucleophilic addition. We said it was a lone pair on the oxygen attacking the carbon of the carbonyl. So basically, we have the oxygen of the hydroxy group forming a bond with the carbon in the carbonyl. Now, what is different here is that we have 2 hydroxy groups. So I'm going to start with my ethane 1,2-diol. So I'm going to start by drawing the chain part of that. And we know that we can be confident that the 2 oxygens that were attached to that carbon, the 2 oxygens from the OH groups will still be attached to their carbons. And at the beginning, it was nucleophilic addition, and it was a lone pair on the oxygen attacking the carbon of the carbonyl. And so both of those, I think we can be confident, are going to be attached to a carbon. So if we think about what we've done here, so there's our ethane 1,2-diol. That comes, I think we can be pretty confident, comes from our ethane 1,2-diol. So the other carbon, the thing I haven't highlighted yet, must come from the ethanal. And ethanal is, the eth tells us it's a 2-carbon chain. So sure, we've got to make sure that we've got the CH3 that would be in at the start. And then if we, carbon always has 4 bonds anyway, but let's just think about it. How many carbons have we got at the moment? We've got 4. How many oxygens we got? We've got 2. But how many hydrogens we've got? We've got 7, and we need 8. So there we go. Sorry. So then I think what we're looking at then is our ethanol is provided this part of the molecule. And just, to help our sort of clarity and understanding, we said we got H2O. And I think we can be thinking that both the hydrogens came from the diol and the oxygen came from the aldehyde. And there we go. There's our answer. It's not easy. You might even be puzzled even having gone through it like this. I appreciate that. But it is absolutely a challenging question. So I wouldn't worry too much about it. So I hope that was useful. Let me know if you've got any queries. And yeah, the next question will be up online sometime shortly.